Hello and welcome to this video on quantities and units. So we're going to be talking from chapter 2, we're going to be talking about quantities and units here. So let's go ahead and get to it. Um, I've had to kind of change how I'm doing this because I had a problem with my other software. Uh, okay, so let's take a look at this. Let's get some definitions here. First off, let's give a few definitions. What is a quantity? A quantity is something that is measurable. Anything that you can measure, once you measure it, then you that is a quantity. Okay. It is something about something that is measurable. All right. So, for example, if you're measuring the length of your notebook, it's not the notebook that is quantity, but it's the length of the notebook that you're measuring. So you can measure several things on your notebook. You can measure its length, you can measure its width, you can measure its temperature, you can measure its mass. All those things are quantities. The notebook is one thing, but things that you can measure about it are the quantities. So it is something that is measurable. It's not the object, it's what you are measuring on the object that is. And when we measure, we need to have something to compare it to. So that's where the term unit comes in. A unit, as you can see on the thing here, on the screen here, the unit is an accepted reference standard, which other measurements are compared to. Okay, and so what does that mean? That means basically we've kind of defined one of something, 1 foot or 1 yard or 1 inch or 1 degree or 1 pound. And then we're going to measure how many of those there are in something. So for example, if you want to go ahead and measure the width of the classroom, let's say then you're going to use feet. Okay. So what you can do in order to do this is you're going to go ahead and take a ruler, which is 1 foot long, and you're going to put it next to the wall, and then you're going to mark at the end of the ruler on the opposite side of the wall um, where 1 foot is. Then you're going to take that ruler and move it over and put the other side of the ruler on the that marking at 1 foot, and then you're going to go ahead and measure away from the wall another ruler length or another foot, and you keep doing that one after the other till you get to the other end of the wall. Okay. What you've done is you've compared the length of the width of the room, how long the width of the room is, to your ruler, and then you say, oh yeah, the room is 12 feet long because it took 12 ruler lengths to get to the other end. Okay, so the unit is that base length that we're using. Right? So we call that the the unit. And it could be 12 feet, could be 57 feet, It could be even a fraction of a feet, could be a quarter foot, or a lot of times, things are really small. We have inches, which we measure, and it could be a half inch, a quarter inch, something like that. All right, so units are basically something that everybody's agreed on. Okay, this is a foot, or this is a mile, or this is a degree. And then you just count how many of those are. That way, when everybody counts, it's about the same thing. Which brings us to the third one down here. The third bullet point is SI unit. And SI unit, what is an SI unit? There's specific units that are part of what we call the International System of Units. Okay. It turns out that science is done throughout the world, and in order for everybody to kind of be able to compare their results, compare their measurements, people had to agree on a certain system. What system of units were you going to use? So they agreed on this system of units, and we'll talk about those, what units they are. It's mostly, if you heard of the metric system, it's mostly the metric system and a few others. On top of that, that is your international system of units. Now, you might say, but Mr., if it's the international system, why is it SI? Because, in the international system, I comes before S. So, why do we call it SI? Well, because when the scientists met to agree on this, they chose French to be the language that they were going to be talking about units and stuff in. So it's not really international system, it's Système International, okay, which in French is international system. It's like in Spanish, it would be also Sistema Internacional if you know Spanish. In French, it's kind of the same thing. It's first système, then international, even though we in English say international system. So since they adopted French as the language for all this stuff, it goes SI versus IS. So when we say it's SI units, we're talking about the international system of units. Okay, so let's take a look at some examples of units. This next chart right here I have are select quantities and units. And by select, I mean they're just a few of them. They're not all of them by any means. So what I have here is a table with 3 columns. Column 1 has different quantities. Column 2 has SI units because those are the ones we're going to be using in science. And the column 3 is going to be English units. Now let me start with column 3 because you might go, well, why did I include English units in there? What do we care about the English units? Actually, English units are the units that we use here mostly in this country. And actually, English units are just about only used in this country. Just about everybody everywhere in the world has gone to the use of metric systems. So if you go over any border, if you go to Mexico, you go to Canada, suddenly mile markers are not going to be in miles anymore. They're going to be in kilometers. So distance will be in kilometers, and people will be weighing stuff in kilograms and things like that. If you look at this chart right here, it shows that these are the countries that don't use the metric system. And as you can see, there are 3 of them. One is the United States. This up here in the upper left corner is our state, Alaska. This one I think is Liberia in Western Africa, and then I think this is Myanmar here in Southeast Asia. Those are the only 3 that don't use the metric system. I think only 2 of them actually use the English system. The English system was a system that when the English went out and colonized all kinds of countries, the English went ahead and used their system in their colonized countries, including the United States. We got used to it. We used things like, as we can go back to here, feet, miles, yards, gallons, cups, things like that, pounds, and we've gotten used to it. The English were using it, and then all their colonies were using those for a while. It's just that people got used to using these units, but eventually along came a better system, and we'll see why it's better in a little bit, called the metric system, and people started adopting that. If you want to look back at this chart here, you'll notice even the English, here's England right here, even the English don't use the English system anymore. Everybody else uses metrics for the most part, okay? The metric system. So scientists use metric system and we get used to it, but we are used to the English system, so I'm bringing up the English, and we will sometimes have to convert our English units into metric units, right? You measure 72 feet, well, how many meters is that? Now you have to convert them, and we will have a lesson later on this week on converting units. So let's take a look at some of the quantities. Length, how far it is from point A to point B, whether it be something relatively short like the length of a tabletop, or whether it be something longer like the length of distance between here and San Francisco. Okay, so that any lengths, no matter how small or how large, as long as you're going from measuring from point A to point B, the distance between those 2 points, that is a length. Volume, how much space something takes up. Mass, we saw that the definition of mass is how much matter is in an object. Weight, how much force the earth is pulling down on it and is acting on mass. Temperature, how hot something is or how cold it is, we can measure that. We can measure time, and we can measure energy. As you can see, there are some characteristic units. For length, in the English system, we use feet, miles, yards, inches, furlongs. I mean, there's more, but I just put a few of them here, just so you're familiar with them. In the metric system, or the SI system, we use a thing called a meter. That's where the term metric system comes in, because it's based on a thing called a meter. And I think they define the meter as like 1/10,000,000th of the distance between the equator and the North Pole, or something like that. They got the distance and divided it. I think it was 10 million pieces. Yeah, because I think it's like 10,000 kilometers there, but then you turn into meters, it's 10 million. And then everything else is based off of that. Centimeter is 1/100th of a meter. So it's based on the length of a meter. It's just 1/100th of that. Kilometer is 1,000 meters at a time. So those are examples, and we'll take a look at the metric system in more depth later on in this video. For volume, how much space something takes up, we have things like gallons and ounces and cups. In the metric system, we have things like liters, milliliters, right? You've seen 2-liter bottles, milliliters, meters cubed. Actually, volume is very common to have cube units, and not just in the metric system, but even in the English system. So remember that a volume, a lot of times we can find a volume by taking the length times the width times the height of something. So if you're going to take a length in meters, a width in meters, and a height in meters, well, you multiply the three numbers to get how many there are, but the units are meters times a meter, or a cubic meter, which is a volume of 1 meter by 1 meter by 1 meter. So that's your unit for volume. You can do it with feet also, feet squared, feet cubed. You can do it with centimeters cubed, and actually centimeters cubed are what in the hospitals they call cc's. So things like that. Masses units, they're in grams, or kilograms, or milligrams. In the English system, some people think that, well, if mass is in units of grams and kilograms, that must mean that in the English system it's pounds, because people tend to convert pounds to kilograms. We say how heavy we are here in this country, yet we go to another country and then they tell us in kilograms, so we think they're the same thing. But it turns out that pounds are actually weight units. So when we're telling somebody how many pounds we are, that's a weight. When they're telling us how many kilograms they are, they're telling us their mass. And their mass wouldn't change in another country, in another planet, but our pounds would, as we talked about in chapter 1. Right? So it turns out that we're converting. I mean, they're related. So there's a conversion that you can just use a certain number you can use to turn your mass into weight in this SI units. So don't worry too much about that. In the English system, we have what's called a slug. And the slug is the English unit for mass. That's the counterpart to the gram. I've never used a slug. It's just know that that's what the English equivalent would be to a gram. But even when I took physics classes, I never used a slug. Newtons are actually the unit of weight in SI, or metric. They're the counterpart to pounds. And newtons are named after Isaac Newton. And they've been defined based on a formula for force. Temperature, we're used to Fahrenheit, degrees Fahrenheit. So if you tell somebody, oh, it's a beautiful day, it's 72. But if you tell someone in another country, oh, it's a beautiful day, it's 72 degrees today, they're going to go, what? It's on fire over there. How can you stand it? Because it turns out that a 72-degree Fahrenheit day is the same as like a 25-degree Celsius day. So they use degrees Celsius elsewhere. Some people call it centigrade because there's 100 degrees between the freezing point and the boiling point of water. So because 100, they call it centigrade, but most people will call it Celsius. And so 72 degrees would be something like, what, 170 degrees in Fahrenheit. Yeah, if you had a 170-degree day around here, you'd think it was pretty hot too. There's also a thing called Kelvin, a unit called Kelvin. And this Kelvin unit is actually pretty important. It actually ends up being the SI base unit. We'll talk about base units next. But so these are units that are common. Time, there's no difference. Looks like the time units that we use, seconds, minutes, hours, days, work, whether you're talking about the SI unit or SI system or the English system. And energy, some people think, well, you can measure energy. Yes, there's actually a way of measuring energy. I will learn how to do it in chapter 16 when we talk about thermochemistry. You may not know how to do it yet, but you are probably aware of its units, calories. And when you talk about calories in food, that's what you're talking about. How much energy is in that food? So you are trying to you're trying to check how much energy is in there, and if you took enough energy in, to be able to expend it, then you don't gain any weight. If you took more calories in, more energy in than you can use, then the excess gets saved as flat fat. And then in the SI system, there is the joule. This one's named after a guy named James Prescott Joule, just like the Newton's named after Isaac Newton. So this one's named after James Prescott Joule. By the way, the calorie, this is not the same calorie exactly that you find on the food packaging. It is, but it's kind of not really a calorie. It's a kilocalorie on food packaging. A kilocalorie is 1,000 calories. But they didn't want to put all the number of calories that were on the food packaging. So if you notice on food packaging, when you read the calories, the calorie will have a capital C. Notice that this has a small lowercase c. On the food packaging, there's a capital C. And that capital C implies a kilocalorie, 1,000 calories at a time. Why? Well, it's marketing. They didn't want to write down that, oh, this food item, this Snickers bar has 220,000 calories. So they put 220 calories with a capital C, implying that there is 220 kilocalories. Okay. So yeah, I will expect you guys to kind of connect which units go with which quantities. So in the future, if I don't tell you, well, the mass of this ball is, if I tell you you have a 12 kilogram bowling ball, you will know that I'm talking about mass. I don't have to tell you it's mass. The fact that that there's units of kilograms. I mean, you're not going to use kilograms to measure how long the ball is, right, or what the circumference is, or how hot it is. So you should know which units go with which quantity. You're not going to measure how long the distance between here and let's say Arizona by giving me a temperature. There might be a difference in temperature between Arizona and here, but that's not going to give me a distance. That's going to give me a temperature difference. Okay, so let's go ahead and take a look at what we'll call base and derived units. Base units are the most basic units that are that are measured, and we can make a whole lot of other units based on these 7 base units. Actually, we're only going to see 5 of them in this class, but there are 7 base scientific units. So let's go ahead and talk about them real quick. Some of them we've seen, some of them we haven't. Um, the base unit for quantity in the SI system, the International System of Units, is meters. Everything's based on a meter. And you can use larger or smaller units. If something's really small, you don't want to use a meter, you want to use centimeters or millimeters, which are smaller units, then you can. We're not saying that you can't use it, but those are based on the meter. Right? Centimeter is 1/100th of a meter, and we'll talk about that in a little bit. And a millimeter is 1,000th of a meter, right? Or a kilometer is 1,000 meters at a time. Okay, so for measuring length, we use meters as the base units. Doesn't mean we can't use other units, but those are our base units. Mass, we use kilograms. Some people think, well, we should probably use grams, right? Because that has no, later on you're going to find that a kilo is a prefix that we use to measure 1,000 of something at a time, like kilometers is 1,000 meters, kilograms is 1,000 grams. But turns out that a gram is pretty light. It's the mass of like one large paper clip, not the small one, but the larger one that you see in your classroom. And so most things, well, are not that light. So most things are kind of about 1,000 times that weight and even bigger. So we use kilograms as our base unit. Time, they're going to use seconds. Like I said, you can use hours, minutes, days, but the base unit is seconds. Okay, that we'll use seconds as much as we can, especially when making new units, as we'll see in the next slide. Temperature in Kelvin. We'll probably use degrees Celsius the most, but when we get to chapter 16, you'll see why Kelvin is the base unit. Kelvin is the only unit that temperature unit that does not have a negative number. And it's not the fact that we're trying to avoid negative, it's the fact that we're trying to keep proportions proper between energy and temperature. And we'll go into that later on. It gets a little complicated, but Kelvin is your base unit of temperature. You can still use Celsius. You can even still use Fahrenheit, but Fahrenheit's probably not going to be found in too many of our equations. So know that Kelvin is the base temperature. For quantities, when you're counting stuff, we use a thing called a mole. And we'll definitely see the mole a lot second semester. Probably not much first semester, but we probably won't define it until we start second semester. Mole is a big old chunk of stuff. And when we use units for quantities already, we use things like pair, the term pair, and dozens, or gross. A gross is a dozen. So, we already use these terms for quantities. Well, we'll get into mole. Now that we just went over scientific notation, I'll just let you know mole is 6.02 times 10 to the 23rd of something. I kind of put that number up in your lesson earlier. And the reason I use that one is because that's the quantity that we use. So that's your SI base unit of quantity. Electric current and luminosity, luminous intensity, we're really not going to use that much. This would be more in a physics class, how much electricity goes through something and how bright a light is. But A stands for amperes, CD stands for candelas. So those are your SI base units. Let's go on to the next one. Now, there are derived units. There are derived units, and derived units are units that we get from the base units. So the way this works is that, there's a lot of quantities that actually can be calculated by using a formula. And when you use the formula, then you plug in the numbers and you end up with units from the quantities inside the formula give you the units for your overall quantity, your derived quantity. So for example, area. Area you guys know is length times a width. Okay. Well, what is a width? A width is just a length in 90 degrees from the original length, right? So really it's two lengths, one in one direction, another one in a perpendicular direction. So I would say that an area is basically just a length squared, or at least there's a length times a length. So as far as units are concerned, it's going to be a length unit in one direction and a length unit in another direction. So all you're going to do is take those units and square them. So if you take a meter in one direction and a meter in a perpendicular direction, you're going to end up with meters times meters, right? Let's say something is 3 meters long, wide and 4 meters long. 3 meters times 4 meters is 3 times 4 is 12. And the units are meters times meters gives you a meter squared. Okay, so meters squared are derived units because they come from the formula where if you go ahead and plug in meters in your formula to the length and the width, in the end, when you multiply those, you end up with meters squared. Okay. Same thing with feet. You can measure things in feet in 2 dimensions, 2 directions, and you end up with feet times feet. They don't have to be the same number of feet, but the fact that you're multiplying feet in both sides means that units, you can treat units just like a variable, right? And so when you multiply the 2 units together, you end up with feet times feet gives you feet squared. Just like x times x gives you x squared. Or y times y times y gives you y cubed. Same thing here. Meters times meters times meters gives you meters cubed. And that's why, while I'm bringing this up right now here, I'm actually also talking about the second row here for volume. Volume here is basically a length cubed, right? Length times width times height. And once again, it doesn't just work for things that are perfect cubes where all the lengths are the same number of, the same measurements. You could have, a volume where the length is 50 meters, the width is 20 meters, and the height is 2 meters. So the numbers are all different. But the fact that they're meters times meters times meters, that means that you're comparing it, your unit is going to be a meter cubed, which is a volume that is 1 meter by 1 meter by 1 meter of space. And then your total volume, you're comparing it to that 1 meter by 1 meter by 1 meter. Okay. Same thing with area. Meter squared means you're looking at your unit being a space that is 1 meter by 1 meter. And then the total area is how many of those little boxes that are 1 meter by 1 meter is your whole space. So these are derived units based on the formulas to get areas and volumes. Then from there we can have other units, like for example, a liter has been defined as, the liter was defined as a space that takes up 1 decimeter by 1 decimeter by 1 decimeter. A decimeter is a tenth of a meter. And so 1 decimeter by 1 decimeter by 1 decimeter is a cubic decimeter. And we said, well, whatever's a cubic decimeter, we'll call that a liter. So we defined it as that. Now, same thing with a milliliter. A milliliter is 1 centimeter by 1 centimeter by 1 centimeter. So if you see this here, cubic centimeters, and this here, milliliters, they're the same thing, except that instead of using cubic units, we just decided to define it as, a thing called a liter. These next two come from equations that have division in the equation. Units for velocity. You guys know how fast you going? Well, I'm going this many miles per hour. And so we always see it as mph, but that's really not scientifically or mathematically a good thing to do. So velocity is distance divided by time is the formula. So if you want to see how fast you're going, you take the distance you've covered divided by how long it took to cover that distance. That's your distance divided by time. So if you plug in a distance, it could be in miles, it could be in meters, it could be in feet, divided by a time, it could be hours, it could be seconds, whatever it could be, that will give you the units for velocity. Right? So if I plug in miles in my distance and hours in my time, I get miles per hour. And what this tells me is that if I have units of miles per hour, it tells me if I were to go an hour at this speed, this is how many miles I would cover. So if I'm going 70 miles per hour, what that tells me is in 1 hour, the unit on the bottom, we're going to assume 1 of it. So in 1 hour, I will cover 70 miles. If instead of using miles and hours, I just measured something for a second and I saw how many meters it covered. So let's say we threw a baseball and in 1 second, here's my meters per second, we measured how far that baseball went in 1 second and it covered, let's say, 30 meters. Then we would say that that ball was going 30 meters per second because it covered 30 meters in 1 second. So we're assuming that in one of the denominators units, the number in front that's how many of the numerator units, right? Acceleration is got in the formula of velocity change over time. I put v, but it really should be delta v. Delta means change, how much you've changed, right? When you accelerate, you go from one velocity to another. If you're standing still and then you speed up, that's acceleration. Or even if you're going 50 miles an hour, you go up to 70 miles per hour, that's an acceleration, right? So you're looking at the change in velocity. So for this one, the units are, let's say, most common units, SI, meters per second squared. How do we get meters per second squared? Well, remember that the units for velocity was meters per second. That's in the numerator. So you have meters per second, and then you divide it by time, how fast it took to make that change. You could have gone from 50 meters per second to 70 meters per second two separate times, but the first time you did it much faster than the second one, so it took less time. So your time is smaller, you'll end up with a faster acceleration because you're dividing by a smaller number. So you actually end up with meters per second, which is our velocity units, divided by, well, the time was in seconds. So if you put those together, meters per second, you end up with meters per seconds twice in the denominator, or meters per second squared. So that's how we get those. Another way, if you're using miles per hour, you divide by hours. How does the miles per hour, how does the velocity in miles per hour change? Divided by another hour and you get miles per hour squared. You probably hardly won't see that. Force is the formula that comes from a formula that says mass times acceleration. So if you take a mass, kilograms, and you multiply by the acceleration, which we already just found out is meters per second squared, your units for force is going to be meters per second squared times kilograms for mass. you're going to end up with kilograms times meters over seconds squared, right? Your acceleration units times your mass units. And then that looks like a whole bunch of gobbledygook. So what people did is they said, oh, we don't want to always say kilograms meters per second squared, so they renamed it the Newton. 1 Newton is when you have 1 kilogram meter per second squared. Similarly to the joule came from the fact that the units are all over the place for this. Energy is in joules, and energy is defined as a force over a distance. So if you put a force over a certain distance, you expended a certain amount of energy to do that. The longer you put that force, the more energy you're going to expend. So since the units of force are kilograms per meters, kilograms times meters per second squared, then you're multiplying distance, which is just a meter, you're going to end up with kilograms per meter squared over second squared. People didn't want to say that. They just kind of left it at joules. They renamed it the joule, I guess you'd say. And the last one we're going to talk about later on this week or next week, it's a property called density. Density is mass of an object divided by its volume. And so mass, you can go ahead and get grams or kilograms or slugs. Well, we're actually not going to use slugs. Usually it'll be grams or kilograms in the numerator. And the volume could be liters or liters or meters cubed or centimeters cubed or milliliters. One of the most common ways of using density is grams per milliliter. What it's telling you is that this little piece of object, whatever you had, if you have 1 milliliter, it's going to weigh this many grams. And remember that I just mentioned up earlier, a cubic centimeter is the same thing as a milliliter, so these here units are about the same thing. It could be kilograms per milliliter, it could be kilograms per liter, it could be grams per liter. It really depends on what the appropriate units for whatever situation you've got there. So, but the main idea here is these are derived units. The units that we got here came from us plugging in the base unit here, these guys, plugging them into these equations, and when those units don't cancel out, you end up with a derived unit, meter squared, or foot squared, or meter cubed, or centimeter cubed, or a meter per second, or a meter per second squared, or a kilogram meter over second squared. Just by plugging in all the base units into this equation and this equation, you ended up with all that gobbledygook. And we redefined it as a Newton to make it easier. Same thing with a joule. But when we look at density, you're going to have to get used to grams per milliliter. Okay, so let's get to talking about the metric system. So as I showed you before, the metric system is used throughout the world. And as I mentioned, when I talk to my family in Mexico, they always talk in meters, centimeters. I'm not 5 feet 8 inches tall in Mexico. I am 170 centimeters, or 1.7 meters. So most of the world uses the metric system. My family's enjoyed going up to Canada the last few years, up to Vancouver. Go from Seattle to Vancouver. It's nice during the summer. But yeah, once you get into Canada, everything's in kilometers and meters and degrees Celsius. So let's take a look at how this system works. I'm also going to put up another video on it because this is very important to understand how the metric system works. We're going to be converting. You'll be getting problems where the formula will ask you to plug in a meter, and you'll be given centimeters. You'll be given kilometers, and you have to turn it into meters so that the formula will work, so you get the right number and not some crazy answer. So let's take a look at how this works. The metric system is a system of prefixes that creates, from one unit, it creates many units based on the power of 10. So it's based on powers of 10. It's basically based on a decimal system. Let me show you how this works. Okay, so if you take a look at this chart that I have here in blue, right here in the middle, we're going to start in the middle. Don't start at the top, don't start at the bottom. Start in the middle right here. This row right here in the middle is what we call our base unit. And the base unit could be any unit that you are using to measure a certain quantity. Okay, if we're measuring the distance, we'll use the meter. If we're measuring mass, we'll use the gram. If you're measuring volume, we'll use the liter. If you're measuring time, you can use seconds. It works with just about anything, but we tend to use it with uh, metric units, meters, liters, grams, things like that. Now, I know I said that the base unit for mass is kilograms, and actually it's going to turn out that kilograms comes from being put on a certain place on this thing from this kilo row right here. But let me explain how this works. We're actually going to, when we talk about the metric system, we're going to use the base unit for mass as grams, even though most scientists use kilograms as the base unit, only because grams are so small. That you hardly ever measure things in grams unless they're pretty light. Most things get measured in kilograms, but we'll use grams as the base unit. So on this chart, what I have here is I have a column that's this prefix. So these are the prefixes these are little words or partial words that mean certain numbers, and the numbers are right here. So here's your prefix, here's the number it means. I called it an equivalent. So what does these prefixes mean? Here's an example. When you put it together, when you put a prefix together with a base unit, it looks like this. And then here's the equalities. In other words, what does each base unit look like? So I'm going to talk first about the units that are bigger than the base unit. Then we'll go to the units that are smaller than the base unit. All right, so you put your base unit here. Let's say we're going to use meter. Meter is going to be your example right here. So we're going to be measuring length. We have a meter, and we've defined what a meter is. And as I told you, a meter has been defined as 1/10,000,000th of the distance between the North Pole and the equator, or at least it was back in the day. And then they just took the distance between the equator and the North Pole, divided into 10 million pieces, and what came out was a distance that's about 3 1/3 feet. All right, so that's our base unit. By the way, the definition of the meter has been refined now, so that, because basically the Earth as it goes along does actually change a little bit, and so that would mean the meter changed. So they got some property of light that will always be the same, and they define that as a meter now. But that's how they first got it. So that's a meter, right? Like I said, it's about 3 1/3 feet. So if you put your arms out, maybe not stretched out, but arms out, you can probably say that's about a meter. So there is a prefix above this. The prefix above it is deca, and as you can see right here, oops, I can't get that. Deca means 10. Okay, so here's the prefix, here's what it means, and here is the shortening of it, so that when we go ahead and use it in the unit, we use these symbols here, capital D, lowercase a, and we put it in front of the symbol for the base unit. Meter, we use the letter M for that. And so when I put DA in front of M, no, it doesn't spell out damn. I mean, it does, but that's not what we're talking about here. It's a decameter. This means a decameter. And a decameter is 10 meters, and I have that right here. 1 decameter is 10 meters. Okay, so you put 10 meters out there, and you got a decameter, right? A decameter is, a little bit more than 10 yards, a little bit more than a first down, maybe 11 yards on a football field. So that is a decameter. You can put deca in front of anything. Decagrams would be 10 grams. Decaliters would be 10 liters. A decasecond would be 10 seconds. Okay, so this system works with just about any unit you want. You want it 10 feet? That's a decafoot. A decafoot is 10 feet, but we really don't use deca with feet. It's not people haven't got used to using it, but it can be used that way. The prefix hecto means 100. So a hectometer, so once again, a hecto means 100. A hectometer is 100 meters. So if you want a bigger unit, let's say maybe the distance between, I don't know, from the goal line on a football field all the way to the other end of the football field, not just the goal line, but actually to the back of the end zone, you know what that is, that would be about a hectometer long, right? So we basically have, meter, once again, is just like, having your hands out, not completely spread out, but having your hands out. A decameter is probably going across the room, classroom. Hectometer is football field, right, from one goal line all the way, not to the other goal line, that would be 100 yards, but 100 meters would be to the back of the end zone. To the end, there's that end zone that's about 10 yards. So that's about a hectometer. Then there is kilo. Kilo means 1,000. And so a kilometer means something that's 1,000 meters. And that's what kind of we use instead of miles in the metric system, we use kilometers. It's not quite a mile. It's actually only like 2/3 of a mile. Technically, I think it's 0.62 miles. But it's still a long distance, and it can be used. So, instead of, saying it's 62 miles from here to there, it's actually 100 kilometers from one place to the other. And so that's about 1,000 meters. And so, think about what 2/3 of a mile might look like. That's a kilometer. So you'll notice that between the base there and what we just hit kilo, there are 3 units. So there's the base unit, meter, then the decameter, then the hectometer, and the kilometer. Each one is 10 times bigger than the previous one, right? 1 times 10 is 10, 10 times 10 is 100, 100 times 10 is 1,000. So every time we move from one to the next, what do you call it, a row up here, we have just jumped its value to 10 times. Excuse me. You will notice that above kilo, there are 2 other units, mega and giga. And between these units, there are black lines. There are bold lines, or there are black lines all over the place here, but there are bold lines. The reason they're bold lines is because now the jump from one prefix unit to the next is not 10 anymore. It is actually 1,000. Okay, so you'll notice that the prefix mega means 1,000,000. And the prefix giga means 1,000,000,000, and we use capital M for mega and capital G for giga. So going from kilo to mega, you're not making a jump of 10 times anymore. You're making a jump of 1,000 times, because 1,000,000 is 1,000 thousandths. And then going from mega to giga, you're making another jump of 1,000, because a billion is 1,000 millions. So we could come up with bigger units than a kilometer, and that would be a megameter and a gigameter. And I guess a megameter would be 1,000 kilometers, whatever 1,000 kilometers might be. Sounds like it's like from here to maybe, I don't know, the other side of Arizona. Sounds like it, right? Because I think that it's about 500 miles to Phoenix. And so if we want to make it 620 miles, that's 1,000 kilometers. Then we'd have to go a little further than Phoenix, maybe close to the border between Arizona and New Mexico. So from here to the border between Arizona and New Mexico, a little bit closer, roughly is a megameter, to give you an idea. And then a gigameter is, well, 1,000 of those. And I'm not even going to give you an example of that. That's starting to get a little bit bigger, and I'd have to kind of think about it. I'm sure I can come up with it, but I didn't think about it before I started doing the video. So I'm not going to spend time doing that. Okay. And once again, you can use these prefixes. So it doesn't just have to be meters, decameters, hectometers, kilometers, megameters, and gigameters. It could have been grams, decagrams, hectograms, kilograms, megagrams, and gigagrams. Actually, we use them in computers all the time already. We have a base unit of bytes, right? And a byte is a little piece of information. It's actually 8 bits of information. And I don't want to get into the whole bits and bytes things in computer science. So basically, one chunk of information, smallest chunk of information that is unique is a byte. You can have decabytes, hectobytes, but usually you see kilobytes. You'll have some files that are kilobytes. They're generally smaller files nowadays, although when I was younger, they used to be bigger files. That's 1,000 bytes at a time. megabytes, which is millions of bytes at a time, and your pics usually are in megs or short for megabytes, and gigabytes. We have storage in gigabytes. We even have storage now in terabytes, which is not only a billion, but tera means a trillion. I didn't put it up here. Capital T is tera. And it's actually common to have terabyte hard drives nowadays. So see how we use these prefixes with bytes instead of meters? We could have used it also in grams. So substitute a base unit, G for grams, and just substitute the G all the way up here instead of the M. And those will work also. The relationships will work also. 1 decagram is 10 grams. 1 hectogram is 100 grams. 1 kilogram is 1,000 grams. 1 megagram is a million grams. 10 to the 6th is a million. And 1 gigagram is a billion grams. 10 to the 9th is a billion. Okay. All right, so that's the relationship there. Below the base unit is the smaller units. And when we talk about smaller units, we're talking about the prefixes deci, centi, milli, micro, and nano. Okay, so deci, when we went above the base unit, we got bigger by 10. As we go down below the base unit, we're going to get smaller by 10. We're actually going to go down tenth to tenths. So a decimeter is 1/10 of a meter. Similarly, a decigram is 1/10 of a gram. Centi is 1/100th. So a centimeter is 1/100th of a meter. Milli is 1/1000th. So a millimeter is 1,000th of a meter. You can take a meter, break it up into 1,000 equal pieces, and each one of those is a millimeter. And that's usually used to measure a lot of very small things. But when things are really, really small, we get down to the micro and the nano range. Micro means a millionth. A micrometer is a millionth of a meter. And if you look at the symbol that we use for micro, it's probably a symbol that doesn't look familiar to you. Maybe it does. It looks like a U, but it looks like a U with a little hanging thing off of on the left side. Right. Here's your micro. That is a Greek letter mu. It's kind of like a Greek M, but lowercase. So it's a Greek letter mu. And so that's what we use for micro, right? Because micro starts with M, but we already used lowercase m for milli. We already used capital for mega. And we use the capital for the mega, for the big one. And we use milli for the smaller one. So there's no more m's left. We use capital M, lowercase m. So they use the Greek m, mu. Okay. Sometimes on like medications, they'll give medications in micrograms, but they won't use mu, they'll use mcg. So maybe I'll add that in here. Oh no, what did I just do? I don't want to lose my mu. So okay, trying to fit this in here. So you might see it like this with medications. And that makes it a little confusing because, yeah, in science we use the mu, and so you'll see it like this, but a lot of, the drug companies aren't going to put mu here. They put MC to make it different from M. And then the bottom over here is nano. N is a billionth. Okay. Now, one thing to notice over here is that I could have put, 1 decimeter is 0.1 meter, 1 centimeter is 0.01 centimeter, 1 meter, 1 millimeter is equal to 0.001 or 1/1000th of a meter. But what I did instead, and let me make this a little bit smaller, see if these will all fit. Let's try 24 and see if it doesn't change it. There we go. I put them in terms of trying to keep the numbers above without fractions and decimals. So instead of 1 decimeter equals 0.1 meter, if I multiply 10 to both sides, I end up with 10 decimeters is equal to 1 meter. Right? So if 1 decimeter is 1/10 of a meter, then it takes 10 decimeters to complete the 1 meter. So 10 decimeters is equal to 1 meter. And all I did was multiply for that relationship here. The 1 decimeter is equal to 0.1 meter. I multiply both sides by 10, and I got 10 decimeters equals to 1 meter. Right? because 0.1 times 10 would be 1. And on the left-hand side, 1 decimeter times 10 gives you 10 decimeters. Same thing here. Instead of writing 1 centimeter is 0.01 meters, I multiply both sides by 100, and this gives you an equivalent equality. 100 centimeters equals to 1 meter. That's the same thing as 1 centimeter is 0.001 meters. It's just that I'm going, okay, if I had a meter, how many centimeters in there? If I had a meter, how many millimeters would there be in there? If I had a meter, how many micrometers would be in there? Okay, so this is the metric system. Now, how do we use it? We go onto this page right here, and basically what you're going to see is that sometimes you will be given a measurement in one metric unit, and you'll want it in another metric unit. As I mentioned, sometimes you need to have the right units to be able to put into a certain equation. The equation asks for meters, but you're given centimeters, you're given decimeters, or you're given kilometers, and you need to go ahead and change them into meters for the equation to work correctly. So how do you convert one unit into the other? Real quickly, I'm going to go over this, and at the end, I'll just do some sample problems here. All right, so it says to convert one metric unit to another, you move the decimal one place to the left for each prefix moved up on the chart within the bold lines. So if I go back to this one right here, if I'm moving within the bold lines, if I have given decimeters and I want to turn them to hectometers, when I move up, I take the number of decimeters and then I move the decimal to the left every time I go up, because your units are getting bigger, so the number of those units actually should be getting smaller. I'll do a sample problem in just a little bit. Second rule is this third bullet point here. Move the decimal 3 places to the left for each prefix moved up across bold lines. You'll recall that I put bold lines here because it's not going up one. It's not just going up 10 as it crossed the bold line from kilo to mega, mega to giga, or even from nano to micro, micro to milli. We're actually going up by 1,000-fold. We're getting big. The unit is getting bigger by 1,000 times each time we cross this line. And so, since it's getting bigger 1,000 times, and 1,000 is 10 to the third, it's like actually moving it 3 places over. So every time you cross a bold line up, you move the decimal 3 places to the left. So every time you go up on the chart, you move the decimal to the left. Within the bold lines, every time you move up, you'll go ahead and move 1 to the left. And once you go across the bold lines, you move it 3 times to the left. And you'll notice that back on here, the last two bullet points basically just tell you to move the decimal 1 place to the right for every prefix you move down on the chart within the bold lines, and move the decimal 3 places to the right for each prefix moved down across the bold lines. So whenever we move down, the decimal gets moved to the right, and whenever we cross the bold lines, the decimal gets moved 3 times to the right. Okay. So let's see if we can do some sample problems here. Okay, so let's go ahead and do some example problems. I showed you the chart. I showed you how these prefixes are related to each other in the base unit, but I didn't really kind of do sample problems. I kind of showed you how you can move up the chart, down the chart, and you can scroll back. I don't have that yellow part right now. I have to go on to a separate page. My recording program kind of messed up. I'm using another thing that doesn't allow me to go back and forth between apps. So I had to copy and paste this here. But let me go ahead and show you how you would use it. So I'm going to go ahead and move this. We'll come back to this in just a little bit. Let's do a sample problem. So let's say that you want to go ahead and convert one metric unit into another. Let's say that you were given that you have 0.135 hectometers. We'll use hectometers to begin with. And you want to turn them into decimeters. So the question is, how many decimeters are we going to get out of that? So our first unit here, we're not even going to be with the base unit. We're going to start off with hecto units and then go to deci units. So that's where we go ahead and go over here and use this. So you find hecto and deci on this chart. So here is hecto right here. Oops, I think I have to be able to use a pen. Let's use a pen. So hecto is right here. Deci is right here. And in order to turn hectometers into decimeters, I have to turn hectometers to decameters first. Then decameters to meters, the base unit, right? No prefix. And then once you have the base unit, I can turn it into decimeters. So I'm going to go down 1, 2, 3 times. I'm going to go down the chart 3 times. And according to that page that we saw, that yellow page, said when you go down the chart, you move when you go down the chart, you move the decimal to the left. So we're going to move the decimal to the left, and we're going to move it 3 times to turn our hectometers into decimeters. So let's go ahead and do that. Move down the chart 3 times to the left. So I'm going to take my number. Oh, put the pen back on here. 0.135. So I rewrite this number just like I had it, and I'm going to move. Oh, actually, you know what? My bad. We have to move, since we're moving down the chart, we have to move to the right. So I'm going to go back here and fix that. When you move it down, you have to move it to the right. And how do I remember that? Think of the abbreviation for doctor. When you move it down, the decimal goes to the right. So as you move down the chart, you move the decimal to the right. Okay. I just remember doctor. And then, of course, if you go down, you move it to the right. When you go up, you move it to the left. So since we're going down the chart, we move the decimal 3 times to the right. Go from decimal, between the decimal 1 to between the 1 and the 3, then between the 3 and the 5, then after the 5. So there I've moved it 3 times. And so now I'm going to end up with 135 decimeters. Okay, so there would be my answer. Okay. All right, so that's how you do that. Let's do another one. Let's do one where we go in the opposite direction. We have, let's go ahead and do this one. We're starting off with 42,300. Let's go with micrograms, or this Greek letter mu and grams. Question is, how many decagrams? Grams, decagrams. It's a G. Okay. So how many decagrams? So in order to do this one, let me go ahead and go back over here, and I think I'll erase a lot of this stuff here. I'm afraid to. I knew I was going to do that. Okay, well. Yeah, I'll erase this stuff here. So I am going from, what do we say, micro to deca. Micro to deca, we're going from micro, which is right here, to deca, which is right here. So this time I'm going up the chart, and how many times I'm going over? Well, going here once, but really remember when we go past this bold line, it actually counts as 3. So there's 1, then 2, then 3, then 4, then 5. So every time we move up the chart 1, between the black lines, we move it 1 time. But when you go beyond these dark lines, you have to move 3 times. So we're really going to move 3, 4, 5, 6, 7 times. We're going to move the decimal 7 times. And since we're going up, it means that it's going to go to the left. All right, up means that it goes to the left. So let's go ahead and do that. We have the number 42,300 micrograms. And our decimal is at the end. We're going to move it 7 times to the left to get decagrams out of it. 1, 2, 3, 4, 5, and we run out of digits. So since we have to move it 7 times, we're going to have to include zeros. 6, 7. So we're going to have to add 2 zeros. And we're going to turn that into the first 0 is going to be before the decimal, so the decimal should be end up here. So it should be 2 zeros after the decimal. 0, 0, 4, 2, 3, 0, 0 decagrams. Okay, once again, I apologize for my writing on this little tablet. I figure I'd be more used to it by now, but I haven't gotten there. Okay, so this is how you could go ahead and do these problems. Let me go ahead and see if I could do something here. I'm going to pattern this again. I'm going to do another sample problem, but let's see if I can copy and paste just what I need here. Copy it. And then, so I think that should work here. So I have a new copy here that's not marked on. All right, so that's all you do. You just go from one to the other. It really doesn't matter. It's whether you go up the chart or down the chart, and you kind of jump from unit to unit. Every time you go up one of these, you move the decimal to the left. Every time you go down one, you move the decimal to the right. Go across the dark lines, and you move the decimal down 3. You're going 3 times to the right. Up, you're going 3 times to the left. Right? So if you had something like, let's see, let's do this one. Let's do computer stuff. It really doesn't matter what the base unit is. It's always kind of the same. All right, if you had, let's say you had 1,800,000 kilobytes. How much storage would you need if you knew the storage in gigabytes? And once again, I got a kilo right here, I got a giga right here, so we're working with the numbers over here. So I'm going to turn kilo into giga, and in order to get from kilo to giga, right, we're starting at kilo. We're given kilo. We want to get to giga, prefix. It doesn't matter if they're bytes, or if it was meters, it would be the same thing, or grams, it would be the same thing. We're going to go ahead and go from kilo to giga, and it's going to take 2 jumps across 2 lines, but each of these lines is bold. So you got to go at 1 and then 2. Right, so from here to here is 3 times to the left. From here to here is another 3 times to the left. So it's a total of 6 times that we have to go to the left. And so let's go ahead and do that. We've got 1,800,000 kilobytes. The decimal, it's not put in there, so it means it's all the way at the end. Then we need to move the decimal 6 times to the left. 1, 2, 3, 4, 5, 6. And that means that's got to be 1.8. And I'm not going to put the zeros in. But 1.8 gigabytes. So 1.8 gigabytes is the same as 1,800,000 kilobytes. It's also the same as 1,800,000,000 bytes. That's kind of by definition. So that's how you're going to do these problems. Really, I'm kind of giving you the hard examples of the harder problems. Usually the simpler problems are you're turning meters into centimeters. So you'd have something like this. Go ahead. 0.830 meters equals to how many centimeters? And so what you would do is, so again, you're starting off with meters, and meters has no prefix. So it's going to be right here. It's your base unit. And you're going down to, you're going to end up in centi, which is right here. So in order to do that, you're going to go down 2 rows. So as you go down the 2 rows, then down 2 rows means down means to the right, and down 2 rows that don't cross a dark line means that you're going to do this. You're going to do it one at a time. So you're going to move the decimal twice to the right. 1, 2, and you're going to end up with 83.0 centimeters. Okay, so that's how you do those problems. Okay. If you have any questions, please let me know. One last thing, I'm going to include another video of somebody that uses something that looks like this. This is it's a kind of a little number type line for using the metric prefixes, and I'll let them explain it. Basically, the idea here is that this line here with no number here, no symbol, represents the base unit, and these other letters here represent the prefixes to the units, to the metric prefixes. So this is deca, hecta, killa. Notice that mega is way over here because you need to move the decimal 3 times to the left to get from killa to mega, and giga is way over here also because you have to move the decimal 3 times to the left to get from mega to giga. So you're going to use this type of line to start from one unit, get to the next, and it'll tell you kind of how many times you need to move to the left or even to the right. On the right side, you have deci, centi, milli, micro, once again separated by 3 lines, and micro to nano is also separated by 3 lines. And so there's another video that I'm going to go ahead and include. You can watch that one. Uses this type of line. If you weren't too crazy about using this chart, going up and down the chart, you can use this line. Remember that this one line in the middle represents the base unit, no prefix, that's why there's nothing in there. That's why I put it here as a base unit. And all these letters here represent the prefixes for the smaller and bigger units, all the prefixed units.